So today we're going to start chapter 12, which is titled Stoichiometry of Chemical Reactions. So let's define this word stoichiometry. Stoichiometry refers to the calculation of quantities in chemical equation. It comes from two Greek words, stoichion and metri. Let's first talk about how we interpret chemical equations. Now, in chapter 11, we learned how to balance chemical equations. So any chemical equation must be balanced and it must have the correctly written formulas. Now, if we consider the reaction here, that is the formation of ammonia, where diatomic nitrogen reacts with hydrogen to produce NH3, which we know as ammonia, you will notice that it's balanced with a 1 to 3 to 2 ratio. These coefficients mean or can be interpreted in three different ways. So let's talk about what the coefficients represent. You could interpret the coefficients as moles of the products and reactants. You could interpret the coefficients as molecules, or you could even interpret the coefficients as liters of your products and your reactants. The conversion factor we're going to learn about today involves these coefficients. Now keep in mind, when you're balancing a chemical equation, the coefficients are counting numbers. So like here we see we have 1 times 2 is 2 nitrogens on the reactant side. So here 2 times 1 is 2 nitrogens on the product side. 2 times 3 is 3 hydrogens on the product side, and 3 times 2 is 6 hydrogens on the reactant side. So these are counting numbers, and the significance of that is that the counting numbers have unlimited sig figs. So that will be important when we look at our calculations in a few minutes. The conversion factor we're going to learn about today to add to our conversion factors that we learned about in chapter 10. Remember in chapter 10 we learned how to find the molar mass of a compound, and we learned how to use Avogadro's number as well in a conversion. Well, today we're going to look at a new conversion factor, and we call it the mole ratio. I'm going to refer to it often as the mole bridge because that helps me remember its function. What the mole ratio or the mole bridge does, it relates the number of moles of any two substances in a chemical reaction. The key is you must have a balanced chemical equation to get a proper mole ratio. We use the mole ratio to convert from moles of one substance to moles of another substance using that chemical equation. This is why I call it the mole bridge. Think about what a bridge does. A bridge connects two sides. It allows you to get from one side to the other. Well, the mole ratio or the mole bridge allows us to cross over like a bridge lets us cross from one side to the other. So you can cross from one molecule to another molecule if you have the chemical equation that is balanced. So we're going to go back to the balanced equation that we looked at on the opening slide, the formation of ammonia. And let's just talk about some possible mole ratios here. So if you look at the balanced equation, you see it's balanced in a 1 to 3 to 2 ratio. So let's say we're doing a conversion and we need a conversion factor that has moles of nitrogen on top and moles of hydrogen in the denominator. So what you would do, we see this is the mole bridge. Notice it's mole over mole. So you come to your equation, you see there's 1 nitrogen, so 1 mole of nitrogen for every 3 moles of hydrogen. What if you were doing a problem, though, that needed moles of nitrogen and moles of ammonia to be related? Well, you look at your balanced equation. You have 2 in front of the ammonia in the balanced equation, so 2 moles of ammonia and 1 mole of nitrogen. Another combination that you could use from this balanced equation is to relate the hydrogen to the ammonia. So looking at the balanced equation, there's a 3 in front of the hydrogen. That means 3 moles of hydrogen are going to be needed for every 2 moles of ammonia. So these are counting numbers, and this would be a conversion factor. This is the only conversion factor where you will notice you will have a number other than 1 beside of moles. If you recall, molar mass, it was always the number of grams per 1 mole of the substance. And in Avogadro's number, it was 6 times 10 to the 23rd representative particles per 1 mole of the substance. So in chapter 10, I kept reminding you that in your conversion factors, moles would always have a 1 beside of it. And that was true for molar mass and the Avogadro's number. But if you're using the mole ratio, the numbers here come straight from the balanced equation. So let's look and see how we would actually use this conversion factor in a calculation. So this Roman numeral 2 is called Tyler stoichiometry. So we're a little more advanced than we were in chapter 10. And we're going to first look at mole of A to mole of B calculations. This is a one-step conversion. Our conversion factor will be the mole bridge or the mole ratio. This is what your general setup will look like. I'm going to move this out of the way. So you have your T-chart, and of course your given would be ever how many moles of A, substance A, you have. In our problems that we're doing, A just represents the substance you start with. So it will be a formula, and B would be the substance you're converting to, what you end with, ending substance. Last chapter, we were going from A to A. We never changed our substance. In this chapter, we're going to need the mole bridge to cross over. So here's where your given will go. This would be your given, and it would have moles of A as the unit. And this is your conversion factor. In your mole ratio, moles of A will always go on bottom because you need moles of A to cancel out here. And moles of B would go on top because that's what you're trying to find. This conversion factor comes from the balanced equation. This is our mole ratio or the mole bridge. This allows moles of A to cancel, and you're left with moles of B. So you would multiply moles of B. You would multiply across the top and divide by what's on bottom. Now the problems that we're going to be doing are coming from the notes examples worksheet that I gave you in class. So always double check to make sure your equation is balanced. This equation is already balanced. Now this says if you start with 10 moles of lithium hydroxide, how many moles of lithium bromide will be produced? So notice it mentions lithium hydroxide and then it mentions lithium bromide. All right, so this is where it's going to be important. This is why I taught you in the last chapter to always identify your substance. So we have 10.0 moles of lithium hydroxide. So you're going to put LiOH. And it wants us to convert to moles of LiBr, moles of B. So this is A and this is B, if you go back to the last slide. All right, so we need moles of lithium hydroxide on bottom because we need moles of lithium hydroxide to cancel. We need moles on top, and this needs to be moles of lithium bromide, LiBr. So again, we're going to get these numbers. This is our mole ratio. It comes from the balanced equation. Since this is a balanced equation already, it's a 1-to-1 ratio. This lets moles of LiOH cancel. So obviously 10 times 1 divided by 1 gives you 10.0 for your answer here. Okay, that was pretty simple. Let's look at another example. Here we have a combustion reaction, and I've balanced it for you already because we're focusing on how to do the calculations right now. If you start with 45 moles of ethylene, how many moles of carbon dioxide will be produced? So let's start off with 45 moles, and this is of C2H4. Now again, one thing I always do, I'm going to circle the substances. This is who I start with. This is A, and then I want to go to moles of carbon dioxide. So here's the carbon dioxide. This is going to be substance B. So I'm trying to convert to moles of CO2. So we want to get moles of C2H4 to cancel. So C2H4, moles of that go on bottom. And we need moles of CO2 on top. Now, the mole ratio numbers come straight from the balanced equation. Notice here, moles of CO2 has a 2 beside it. So we pull a 2 from the mole ratio. Moles of C2H4 has a 1. Okay? The moles of C2H4 cancel. So you have 45 times 2 divided by 1. We need to round this to 2 sig figs because the mole ratio numbers are counting numbers. They have unlimited sig figs. So we need 2 sig figs here. So this is going to round to 90 with a decimal to make that count as 2 sig figs. All right, let's look at example 3. You might want to pause the video here and try the next two on your own and then pick up and check them. This says 5.5 moles of lithium